So the electron configurations that we've been talking about correlate to the periodic table. Here's the periodic table of the elements, and I want to emphasize here the columns on the periodic table. For example, let's look at column number 1. Each column is also known as a group. So groups and columns are synonymous, and each of them has a number. In this periodic table, they just have regular numbers going from 1 to 18. Okay, so these columns or groups in the periodic table are a way that we classify elements because elements of the same group or column on the periodic table have similar chemical properties. And the reason is that elements of the same group, okay, and again, when I say group, I mean column, vertical column on the periodic table, have the same outer electron configuration. We have a special word for outer electrons in atoms, and that word is valence. So valence electrons are whatever electrons that are in the outermost or the highest principal quantum level n. So anything in the outermost principal quantum level n, it counts as a valence electron, the highest n value. So let me show you what I mean. Let's take group 1 on the periodic table. I'm going to talk about hydrogen through francium, so this first group on the periodic table. That group of elements that shares the same column, if you look at those elements, starting with hydrogen, going to lithium, sodium, potassium, rubidium, cesium, and francium, and then we look at their valence electron configuration, you can see that the valence electron configuration is analogous going down the column. So here by valence, I just mean outermost electrons. So for hydrogen, the electron configuration is 1s1. For lithium, the valence electron configuration is 2s1. For sodium, 3s1. For potassium, 4s1. For rubidium, 5s1. For cesium, 6s1. And for francium, 7s1. So they have analogous valence electron configurations. And as a consequence of this is very important, as a consequence of this, elements of the same group have similar chemical properties because they have similar electronic behavior. Similar chemical properties. That means they're going to behave similarly in chemical reactions. That means that their electrons will react in similar ways to each other. So this is group 1. I should have emphasized this is group 1. For example, group 1 elements, they are also known as the alkali metals. Okay, so everything in that first column is known as an alkali metal. All want to lose that one electron, their one valence electron, to attain a noble gas configuration. A noble gas electron configuration is extraordinarily stable with all the valence subshells filled. So this is just kind of an explanation for why their chemical behavior is kind of similar to each other, because they all really want to just get rid of this valence electron so they can be like the nearest noble gas. So the other thing about, so that's what we can say about the elements in the same group or column. But when we look at the periodic table, in addition to columns, we have rows. Okay, So let me clean up this periodic table so we can look at it again, because I want to emphasize some information about the rows in the periodic table. The horizontal rows in the periodic table indicate the filling of sublevels. What I mean by that is the following. As I go from group 1 to group 2, that indicates the filling of the S sublevel. As I go from group 13 to group 18, that indicates the filling of the P sublevel. The D sublevel encompasses groups 3 through 12. That's the transition metals. And then finally down here, these lanthanides and actinides, which are kind of inserted here and here, they're just kind of shown on the bottom so that the periodic table isn't too long in the horizontal direction. These correspond to the filling of the F sublevels. So we call groups 1 and 2 the S block. We call groups 13 through 18 the P block. Groups 3 through 12 are the D block. And the lanthanides and actinides are the F block. So, just to make sure that we understand that, I just want to say it again to emphasize that horizontal rows on the periodic table, so not columns, but the rows, indicate the filling of the sublevels. So this is very important. And you can actually use the periodic table to figure out electron configurations in that way. So groups 1 and 2 correspond to the S sublevel. The transition metals are the elements in groups 3 through 12. Those correspond to the D block, the 5D orbitals in a given principal quantum level. And then groups 13 through 18 correspond to the P block. And then at the very bottom of the periodic table, you have the lanthanide series and the actinide series. And those fill the F sublevels. Now, when we are looking at the periodic table, we can kind of use that to derive electron configurations. For example, let's just take phosphorus. Phosphorus would have an electron configuration where its nearest noble gas would be neon, so we can abbreviate its electron configuration like that. Then, this is the third row, so its valence configuration is going to be 3s2 and then 3p3, because we're going to have those 3 electrons in the 3p sublevel. So this would be the electron configuration for phosphorus that we would expect to see. Let me do one more. Let's take, for example, bromine. Bromine is here. Its nearest noble gas, the noble gas above it, is argon. So if we're talking about its valence configuration, we're in the 4s block here. So we have 4s2 that's going to be filled, followed by, this is the 3d block. Remember, 4s fills before 3d, so 3d10, and then 4p, 1, 2, 3, 4, 5. So this would be the electron configuration for bromine. So you can use the periodic table to write down electron configurations for any element.